but it'll be fine. It all starts with matter. Matter is any substance that has a mass. Remember, mass is an inherent constant property of an object, different than the concept of weight, which has to do with gravity. Matter is composed of atoms. Atoms are composed principally of protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. Protons and neutrons live in the nucleus, and they're surrounded by electrons. This is the classic description of an atom, probably based on the logo from the Atomic Energy Commission that was formed in 1946. It has since been disbanded, but as part of their logo, they had this cute little atom in the middle, nucleus, and electrons in nice little orbits around it. The problem is that this is totally wrong. It's totally wrong because electrons really are not little balls in little orbits spinning around the nucleus. It's also wrong because the nucleus is not big. The nucleus is absolutely incredibly tiny. Modern quantum science basically describes an atom like this. We have electrons in a cloud. We know the region of space that this cloud occupies, but we have no idea where the electron is within this cloud, but it's somewhere. The nucleus, this is for helium. Helium has 2 protons, 2 neutrons, and it is minuscule, little teeny tiny thing way in the middle. We'll talk about that in just a second. But let's talk about the basic particles first. An atom is very, very small. If we had a penny made of copper, it would contain 28 sextillion atoms. Now, contemporary pennies have almost no copper in them. Indian head was about 95% copper, so roughly 28 sextillion copper atoms. Tiny little things. A proton. Every atom will have protons, neutrons, and electrons. The mass of a proton has been measured. It's about 1.67 times 10 to the minus 24 grams. Tiny. This number here is scientific notation. If we converted this to decimal, it would look like this. Again, lots of zeros. We're going to do scientific notation in just a minute, but basically we have 23 zeros in front of our 1 here. We've moved our decimal place over 24 places. That's where this comes from. A neutron is darn near equivalent to a proton, same mass. An electron is much, much less, at least 1,000 or more less. Now, this is interesting because this tells us that virtually all of the mass of an atom is contained in the little tiny nucleus in the middle. And the big space around it doesn't contribute much to the mass at all. An element is a substance that contains only one type of atom. Every element is identified by a chemical symbol. The symbol can be derived from the name, or some of the things that have been around for a long time, things that were discovered in antiquity, The symbols are actually named based on Latin or Greek. We arrange these in something we call the periodic table, and this is a crude, simple periodic table, and we don't have one in this room. Maybe that's one if we fold it down, but this is the periodic table. As you see, many elements, easy to identify the symbol based on it. H for hydrogen, Be beryllium, Mg magnesium, C for carbon, He for helium. There are ringers, however. Silver is Ag, gold is Au, Hg is mercury, let's see, Pb is lead, Sn is tin, antimony is Sb. Ones that we see all the time that you need to worry about, P is phosphorus, but K is potassium. That's one thing that people always get mixed up. Na is sodium, but many of these you can just plain guess. Here's a starter list of sorts, elements that we're going to be talking about, and you should be familiar enough with these that you can recognize the element and their symbols. The basic rule is if we talk about something in class, you're expected to know. So if I talk about yttrium, you're supposed to know yttrium is a Y, etc. This is Chemistry 100. We're not going to get stupid with expecting you to know this and that. So basically, just kind of follow along with what we do. There are, however, people that are obsessive and want to know all of them. There are mnemonics that you can memorize, you know, like the quick brown fox jumped over the elements. All right, well, let's go back to our penny and our 28 sextillion atoms. I said that we express these numbers in scientific notation. 28 sextillion in scientific notation looks like this, 2.8 times 10 to the 22nd. This guy, little teeny tiny thing, comes across, like we said, at 1.67 times 10 to the minus 24. Now, converting numbers from decimal format into scientific notation is not difficult. There just are a couple simple rules that we have to follow. What you want to do is take your number, whether it has a real decimal point or not. You want to move either the real decimal point or the implied one between the first two numbers, so that you wind up with something that's between 1 and 9. Okay? Then we're going to see how far we had to move this decimal point in order to do that. If we moved it to the left, our exponent on our power of 10 will be positive. Move it to the right, it's negative. Really simple. Let's say we had 950,000. There's no real decimal point, but the implied decimal point is here. First thing we want to do is put the decimal point here between the 9 and the 5. Then we look at it and say, okay, what do we have to do to get there? Basically, we had to move from here, 1, 2, 3, 4, 5 spots. That means this is going to be 10 to the 5th. And we write the number, 9.5 times 10 to the 5th. Let's do another one. Actually, let's do 5 more. Go ahead and take this whole set and rewrite them in scientific notation. Now we'll do these one at a time, so I'll let you get started. and then we'll talk about them one by one. For our first one, we have a real decimal point. We want to move it here between the 2 and the 5, right? To do that, we have to go to the right 1, 2 places. That means our exponent is going to be minus 2. 2.57, and the exponent 10 to the minus 2. Our next one, we do have a real decimal point. We want it here between the 1 and the 2. In order to get there, we had to move to the left 1, 2 spots. So that's going to be a plus 2 exponent. Now think about this. It just really makes sense. 10 squared is 100, isn't it? 100 times 1.256 is 125.6. So it's really simple. Our next guy, 93 million. Implied decimal point is here. We want it here, so we write 9.3. Now to get there, we had to go to the left, 1, 2, 3, 4, 5, 6, 7. So it's a plus 7. Doesn't matter if it's plus or minus, of course not. We want our decimal point here between the 6 and the 5. To get there, we had to go to the left 1, 2, 3, 4 places, 10 to the 4. And our last one, we want our decimal point between the 2 and the 7. To get there, we have to go to the right 1, 2, 3, 4, 5, 6 places. That's a minus 6. Any questions? All right, let's do it backwards. Take these guys and rewrite them in decimal notation. Here our exponent is positive. That means we're going to move the decimal to the left now. I'm sorry, the right. So it's going to go here, boop, boop, and we just wind up with 257. Now our next one has a negative exponent. So that means we're going to have a whole bunch of zeros here in front. How many? Our exponent is minus 7. That means we'll have 6 zeros and then our decimal point. We're moving it 7 places. That gives us 6 zeros, then our decimal, and we'll always put a 0 in front just because that's good form. And it will look like that. 6 zeros, our decimal, and then a 0 just for good form. (9.3 times 10 to the minus 4). Negative exponent, minus 4, 3 zeros, then our decimal point. Now this one's cute. We have lots of zeros in our coefficient here, don't we? We'll see why in just a while. Has to do with significant figures in a measurement, but that's later. But 10 to the fourth. So we're going to have to move our decimal point to the right 4 places. When we do that, we go 1, 2, 3, 4. So the new decimal point is right here. 65,800.00. And finally, our last one is totally trivial. Is 10 to the minus 1. So we have no zeros. All we do is move our decimal 1 point, put a 0 in front, good form, and it looks like that. Any questions? Now, in this course, it's essential that converting between decimal and scientific notation be so automatic to you that it's like breathing. Okay? So, there's a tutorial to describe this. Lots of practice. It's here labeled scientific and decimal notation. Click on this, and this window opens. What you're supposed to do here, again, this is totally random numbers, so every time you go, you'll get different combinations. But you take this number and convert it to scientific notation. Now we can do that. We want to have our decimal here, so our coefficient is going to be 8.3, correct? Now to do that, we had to move it to the left 1, 2, 3, 4, 5, 6, 7 places, so it's 10 to the 7th. Don't put in plus 7. If it's negative, put in the negative sign, but don't put in the plus sign. It doesn't do that. Quickly, write this one. We want our decimal between the 4 and the 6, so it's 4.6. To get there, we had to move to the right 1, 2 places, so that's a minus 2. It always tells you you're right or wrong, and that when it's right, it makes you feel good, right? Right. Point. Do this one. Here we have a number in scientific notation. You want the decimal equivalent. Well, it's a minus 7, so we're going to put 7, 1 here, and then we're going to put 6 zeros in front. Then our decimal point, and a 0 in front of the decimal point, just for good form. And that's right. Again, if you mess up, click on Show Answer. It'll tell you what you did wrong. Do this again with a plus 7 exponent. Because this is a plus 7, we're going to write our 5.6, and we're going to have zeros after the 6. How many? 6 of them. 56 million. one more here. Go ahead and write this guy. A coefficient is going to be 6.1, isn't it? In order to get there, we have to do 1, 2, 3, 4, 5, 6 places. So that's a -6. Now, doing tutorials is not only fun. It's good practice, makes you feel good, good for your self-esteem, all of that stuff. But we've done 5 of these now, and we got them all right. When you do this online, and you get your 5th one correct, this appears. Email your instructor. You have completed 5 problems, and you can receive credit for it. Oh my goodness. How do you do that? Well, this is me, intro@chemistryonline.com. Don't change that, please, ever. It'll come up automatically. Leave it there. Down here where it says your email, you can put in your Triton email that has your full name in it, or you could just type in your name. Doesn't matter. This will go to me in a special box, and I will look at it and give you credit. What kind of credit? For every tutorial that you complete out of the assigned ones, you will get 5 points added to your first exam. Oh my goodness. Talk about a game changer, right? Everybody wants to go now and sit and start working tutorials. Only the ones that are assigned will give you your 5 points. Not all of them are assigned. Probably 30 over the whole semester. But 5 points per shot. Any questions?
Where do we go to this?
This is chemistryonline.com.
Right. Okay, because I printed up all that.
Right.
So, if we went to the notes that we had, I printed these up on, and we get to that.
Click on tutorials, pick your tutorial. Now that this is really worth some money to you, lots of people get paranoid. You know, did it really go through? Okay, you can get yourself a receipt. Now, you don't have to do this, but you may. If you put your little cursor here in front of the intro, and then type in your Triton email address, put a comma and a space, then hit submit. I will get a copy, and you will get a copy. If you don't get a copy, something went wrong. You want to fix that. Because if I don't get a copy, I have no idea. I have already received from the other class 2 where they didn't put their name in at all. That's not good, because they don't get anything for that, do they? So make sure your name is there. If you want a receipt, put your address in front of mine, comma, space. This works really well with like Safari and Chrome. Remember, Internet Explorer is horrid. Don't ever use that for anything. And don't use some off-brand browser because you never know. But those, the big two, really work nicely. Any questions? All right, let's go ahead and move on to the metric system. These measurements that we take and we use are going to be in metric units. Metric unit of length is a meter. Mass is a kilogram. Don't worry about the volume because nobody uses cubic meters. But what you will do, and we'll see this on the next slide, is we will take a measurement, say in meters, and we will pair that with a prefix. Here's an example. A centimeter has a little c in front of the meter. A centimeter means 10. I'm sorry, it means minus 10 to the minus 2. Okay? 1/100th of a meter. Here's our whole list. These are our prefixes, and basically by sticking the prefix in front of some unit of measure, you are inserting an exponent. So let's say we were looking at a millimeter. Millimeter, M-I-L-L-I, the prefix is a lowercase m. If we have 1 millimeter, and m stands for 10 to the minus 3, millimeter is the same thing as writing 1 times 10 to the minus 3, that's the m, meter. 1/1000th of a meter. So it allows us to abbreviate all of these exponents just with a simple letter. Pico is 10 to the minus 12, nano is minus 9. This is a mu, weak mu, micro it is, and it's minus 6. Milli is minus 3, centi is minus 2, deci minus 1. Kilo is 10 to the 3rd, mega is 10 to the 6th, and gigabyte is 10 to the 9th. You simply pair those together, and it describes your measurement without having to put in exponents. We can also express this as a simple ratio. And I'm doing this because we're going to use ratios in a minute. If I write 1 millimeter, that is the same thing as writing 1 times 10 to the minus 3 meter, isn't it? Exactly the same. I can just put them together in this ratio. This ratio has a value of 1, doesn't it? Because they're the same measurement, top and bottom. All right, ratios are going to be important. If we wanted to interconvert millimeters and meters, we would want to come up with a ratio to allow us to do this. Now remember, milli is 10 to the minus 3, isn't it? So the ratio we just saw is this one. 1 millimeter is the same as 1 times 10 to the minus 3 meter. We can also express it differently and simply say, well, gee, if I had 1,000 millimeters, that's 1,000 times 10 to the minus 3, that's 1. 1 meter, 1,000 millimeters. And because these have a value of 1, these ratios, you can flip them over. So for every conversion, there will be 4 possible ratios you can write. This way and upside down. They all have a value of 1. Now writing these ratios is an important skill. So let's go and do a couple. Give me a ratio for meters and picometers. Now, we just started this, so here's our table. Pico, remember, is 10 to the minus 12. So write me a ratio between picometers and meters. 2 of them, actually. That's actually fairly simple, isn't it? Picometer is just going to be PM. Pico stands for 10 to the minus 12 meters. 1 picometer, pico is 10 to the minus 12, and there's our meter. Now I've done my little thing here. You can also say that if we had 10 to the 12th picometers, that's the same as 1 meter. And of course, you can flip these upside down. Let's do another one. Meter and micrometers. Remember, micro is the Greek symbol mu. 10 to the minus 6. 1 micrometer is the same as 1 times 10 to the minus 6 meters. And here's our ratio. 1 micrometer. Micro is the same as 10 to the minus 6 meters. And if we had 10 to the 6 of them, a million, we would have 1 meter. And of course, flip them upside down. One or two more because it is an important skill. Nanometers and meters. Nano, remember, is minus 9. So 1 nanometer is the same as 10 to the minus 9 meters. And if we had 10 to the 9th of them, we would have 1 meter. Now, you may notice I wrote these upside down because I could. Remember, you can write them any way you want. All right, so we're all skilled now at writing ratios. What in the world are we going to do with them? Well, we're going to use them in an algorithm. It's a problem-solving algorithm that basically, once you master it, will provide you all the math skills you need to get through this course and general chemistry. It's so simple. This is called given a ratio and find. When you have a problem, word problem or whatever, you can almost always look at it and easily say, oh, okay, this is the number I'm starting with. This is the given. I'm trying to find something else. And what I need is a ratio that relates given and find. So, if we were given a measurement in meters and we were asked to find kilometers, we would need a ratio between meters and kilometers. The one thing you have to remember, given the number that is given will have units, right? It's a measurement. It will have units. The units of given must appear in the denominator of your ratio. So let's do a problem. If I say I have 6,023 kilometers, how many meters is that? Well, our given is clearly the 6,023, isn't it? The ratio we want is going to be between meters and kilometers. And of course, we're trying to find meters. So here are a couple ratios. They relate kilometers and meters. Remember, kilo is 10 to the third or 1,000. So 1 kilometer, 10 to the third meters, or you could just say 1,000 meters. Same thing. Which ratio do you pick? Units of given are kilometers, so that has to be in our denominator. So to solve the problem, you write your given. Ratio must have kilometers down below. And the reason for that, of course, is that mathematically, these will cancel. So, you're to the point where you do the stupid math. Pull out your calculator, 6,023 times 1,000, 6.023 times 10 to the 6th. Now again, doing these things just takes practice, and as you do them, it gets simpler and simpler. Let's go ahead and do a set. What I want you to write down for me is simply the ratio. The ratio that we need to convert grams to kilograms. Kilo is 1,000, or 10 to the third. So there will be 1,000 grams in 1 kilogram. Kilo stands for 1,000. Therefore, that ratio would work. This is our given in grams, and grams is in the denominator. So how do you solve the problem? You solve it simply by taking the given, multiply the ratio, and we get 2.057 kilograms. Any questions? Well, let's do the next one. Meters and micrometers. Remember, micro is 10 to the minus 6. Well, meters to micrometers. 1 micrometer, 10 to the minus 6 meters. That ratio would work. Remember, we need meters in our denominator because given has units of meters. The symbol micro stands for 10 to the minus 6, so it just really makes sense, doesn't it? Multiply it out, multiply this by a ratio, and you should get about 0.125 micrometers. Grams to nanograms. Nano is 10 to the minus 9. The ratio must have grams in the denominator. One nanogram is 10 to the minus 6 grams. So you could write a ratio like this, 10 to the minus 9, sorry. And to solve the problem, take your calculator, you multiply this by this, grams cancel, and you're left with 9.3 times 10 to the 5th nanograms. Two more, this is simple. Meter and kilometer, we've done that. Kilo is 1,000. 1 kilometer is 1,000 meters. We must have meters in our denominator, so this would work. 1 kilometer is the same as 1,000 meters. Multiply it out, and we're about 65.8 kilometers. And our last one here, we're dealing with milli. Remember, milli is 10 to the minus 3, 1/1000th. So 1 milligram is 10 to the minus 3 grams. We could write the ratio like this. 1 milligram, 10 to the minus 3 grams. Grams will cancel. Multiply it out, and we get 278 milligrams. Now again, just practice is all it takes. We'll be doing problems that involve conversions all the time, so you'll get lots of practice. Any questions? The last thing I want to talk about in the metric system is temperature. Here in this country, we measure temperature using the Fahrenheit scale for some reason. Just to be different, I think. Water freezes at 32, it boils at 212. In science and in the rest of the world, we use the centigrade scale. On the centigrade scale, or Celsius, water freezes at 0 and boils at 100. Now there is a simple way to convert these two back and forth, but I promise you I will never ever ask you to do that. You will never have to convert from Fahrenheit to centigrade or whatever. Everything we do will be centigrade. Well, not everything. Almost everything. Turns out that there's another temperature scale that's used in science, and that's called Kelvin. This guy. Kelvin. Water freezes at 273 and boils at 373. Now you'll note that there's 100 little spaces here, 100 little spaces here, so the two are easily converted. The 273 thing might seem odd right now, but when we do the chapter on gas laws, it will become immediately apparent why we have to use Kelvin and where 273 comes from. But that's our two. Centigrade, once we get to gas laws, we'll do Kelvin. Any questions? All right, let's do another simple background thing. And this is the concept of significant figures. Science is all about doing measurements, okay? So we're gonna do measurements, and you're gonna tell people about them. Hey, I measured this, it was so-and-so. There has to be a way that you can relay to somebody else exactly how accurate your measurement was. And that is the concept of significant figures. Let's say we have a ruler and an arrow, and you are measuring up to this arrow. You look at it and you say what? Well, okay, that's 50, 51, 2, 3, 4. It's at least 54. We're sure of that. And where is the arrow? It's about halfway. It's about. So what do we put down for our measurement? 54.5. Now, what this tells us is that 54, we're sure of. It is 54 at least. And it's about halfway. This number has three significant figures. First two are real, and the last one is your best guess. If I said 54, clearly it's more than 54, isn't it? And if I said this was 54.66666, that would be stupid, because we don't know that. It's about halfway. Three significant figures, two that we're sure of, and our best guess. So when you look at a measurement, you can always look at the last digit and remember that the last digit is the best guess. The others are real. Only time this gets confusing a little bit is if you have zeros before or after a number. So there are rules for that. Dealing with zeros. First thing you have to do is look to see if your measurement has a decimal point or not. If it has a decimal point and there are zeros in front of your number, those are never significant figures. They're never real. If there are zeros afterwards, yes, that is part of the measurement. Zeros in between, of course, are always real. Now, if your number doesn't have a decimal point, it also won't have leading zeros, but in this case, trailing zeros are never significant. So you look to see if you have a decimal point. If you have a decimal point, leading don't count, trailing do, no decimal point, no trailing. It's actually a real simple process. Let's say we have 3,400. Doesn't have a decimal point, does it? Because it doesn't have a decimal point, the trailing zeros here don't count. 3,400 has two significant figures. Here we have 00010. We have a decimal point, don't we? But all the leading zeros don't count. Trailing zeros, however, do count. And we have two significant figures. Again, we have a decimal point. All the guys in front go away. This zero is between real numbers, so it stays. And we're left with 1, 2, 3 significant figures. $20.50, no decimal point. Get rid of the last zero. And we have three significant figures. Any questions?
Why do you get rid of the last zero and then 20?
If there's no decimal point,
Okay.
trailing zeros are not significant. When this measurement was taken, it was 2000 for sure, 5 or 2000, 0 is real, and then 5 was the best guess. How about this guy, 6.02 times 10 to the 23rd? Well, that's scientific notation, isn't it? If we converted it to decimal, it would look like this. It has no decimal point, so all those go away. And we're left with 3 significant figures. Now, that's the really neat thing about scientific notation. The coefficient contains all of the significant figures, all of them. So if you see something in scientific notation, you know immediately the accuracy of that measurement. Any questions? Well, let's do an exercise here. Let's do 2 things at once. We'll practice writing scientific notation. Step 1, you need to look at the number, decide how many significant figures go in the coefficient, and then write your exponent. Our first one, we have a decimal point, and we have leading zeros that we get rid of. So our coefficient is simply going to be the 3 significant figures, 2.57. To get there, we had to move to the right 2 places, so it's a minus 2, 2.57 times 10 to the minus 3. Our next one has no zeros at all. All these are significant digits. We just have to move it to the left 2 places. That'll make it a plus 2, 1.256 times 10 squared. $93 million. No decimal point, so all the trailing zeros go away. We're left just with 9.3. We're going to the left, 1, 2, 3, 4, 5, 6, 7, so it's a 10 to the 7th. Now look at this one. How many significant figures in this number? Well, there's 6 of them, aren't there? It has a decimal. That means that all the trailing zeros count. So in our coefficient, we need all 6 digits because they're all real. We're going to move our decimal point here between the 6 and the 5. And then we're going to write everything. Our exponent will be 1, 2, 3, 4, so 10 to the 4th. As a decimal point, so the trailing zeros are real. Our last one has a decimal point. All the leading go away. 2.78. Going to the right 1, 2, 3, 4, 5, 6 places, minus 6. Now, you know, when you write exams for courses like this, you can write questions, how many significant figures are there in this and that and whatever. Yeah, you can do that. That gets boring after a while. So one year at USC, I decided not to be boring, and so I put this problem on. Arrange these in order of decreasing number of significant figures. Our first one, we have a decimal, leading zeros don't count. How many? Just 2. Our next one, these are all between real digits, so that's 1, 2, 3, 4, 5. This guy has a decimal, so all these trailing zeros count. That's 1, 2, 3, 4, 5, 6, 7. No decimal, these don't count. 1, 2, 3, 4. A decimal, 1, 2, 3, 4, 5, 6, 7, 8. No decimal, and we're at a 3. So the winner is 1 with 8. What's next? I think this guy with 7. Next, we're going to have a 5, I think. This one's 4. That's 3. And that's 2. Now, most people in the class got it, but I will tell you I don't do this anymore, because can you imagine trying to grade 500-page papers with this problem on it? It was not fun. Now, significant figures. This is everybody's favorite tutorial because it's simple. You look at the number and you tell me how many significant figures there are, and just type the number in. How many? What's the answer here? We have 3. No decimal, 3 digits. How about this guy? Yep, a lot. It's 8. Oh, scientific notation. That's so simple. All you do is look at the numbers in the coefficient. There are 4 of them. And I think 1 more, maybe 2 more. Decimal point, leading go, that one stays, we're at 2. Any questions? Once again, you do this, get 5 right, you got your 5 points. Only can do it once though. Now you can do it 10,000 times, but only send it to me once, okay? That's clutters up the box. All right, let's get out of the realms of measurements and math and stuff like that and talk about some chemistry. We said matter, any substance that occupies space and has mass. Element is the simplest form, a compound. If you take 2 or more elements and you combine them in a specific and constant pattern, you get what's called a compound. This is methane. It has 1 atom of carbon in the middle and is bonded to 4 atoms of hydrogen. The geometry is tetrahedral. Every molecule of methane will look exactly like this. 1 carbon, 4 hydrogens, tetrahedral geometry. That is a compound. Compounds can be broken down into elements, and you can make a compound from elements. A pure substance. Pure substance can be an element, it can be a compound. The only requirement is that it's the same thing throughout. Okay? It's either an element or a compound, not easily separated. A mixture is a combination of substances. We're simply going to take them and put two or more substances together. They're not bonded together, they're just put together. There are two types of mixtures. Heterogeneous mixture is what we typically think about. Think of salt and pepper. Salt, salt. It's just salt. Pepper, all those little flakes. Some are gray, some black, whatever. The other type is a homogeneous solution, homogeneous mixture. If you take and dissolve something, dissolve sugar in tea, for example, they're still separate. It's still sugar, it's still water with this flavoring in it, but you could separate the two. Nonetheless, it is uniform. The real test for homogeneous and heterogeneous is sample. If I take a homogeneous solution and I pull out a sample from here and here, it will have the same composition. If I have a heterogeneous mixture and I pull out a sample here and here, it will be different. For example, gravel, classic heterogeneous mixture. If I took a handful here and a handful here, they're different. This is salt water. Salt water, homogeneous mixture. If I take a sample from this side and this side, they're the same. I can separate them, however, if I let this thing just sit out, the water evaporates, and I'm left with the salt. So it's a mixture. Any questions? All right. There's a rock. Is a rock a pure substance? Well, it's pure rock. That doesn't count. If you actually take a rock and do a thin section, look at it under a microscope, you'll see that it's an aggregate. It's lots of little rocklets squished together. This is clearly a heterogeneous mixture. This sample is different than that sample. Gold bars, they all look different, don't they? However, it's a pure substance because at the atomic level, they're all made up of only one element, gold. This one's a little tricky. This is ice water. Is this a pure substance? Well, it depends on how long it takes you to get the answer. Right now, you could sit and you could pluck out the ice, can't you? Separate it. You'd have a little pile of ice, a little glass of water. So that's a mixture. But if we let it thaw, it would be a pure substance. So as it sits, it's a heterogeneous mixture, even though it's all water. This is sodium chloride, table salt, under a microscope. Little cubic crystals. They all look different, don't they? But again, on the atomic level, it's just sodium and chlorine atoms arranged in a cubic matrix. It is a pure substance. Two different atoms, but still a pure substance. Look at a list. Just run through these quickly in your head and decide if they're pure substances, mixtures, or elements. The air we breathe. It's not pure oxygen, is it? We would all spontaneously burst into flames. It's nitrogen, oxygen, carbon dioxide, methane, all of those things, lots of gases. It's a uniform mixture, and it's homogeneous. Sample of air here and a sample of air here have the same composition. Homogeneous. Ground pepper, classic, lots of little flecks. It's a heterogeneous mixture. Seawater, well, we saw that. Seawater is a homogeneous mixture or a solution. How about sugar? What is sugar? Sugar contains carbon, oxygen, and hydrogen in a fixed ratio and a fixed geometry. It's a compound. It is a pure substance. This is sucrose. This is table sugar. The reds are oxygen, black is carbon, whites are hydrogen. Every molecule of sucrose looks like that. Gasoline. Think about it. You get to choose, do you want high octane or whatever? Octane is just a hydrocarbon, and gasoline is just a mixture of hydrocarbons. The more octane, the faster it burns, but it's still a homogeneous mixture of hydrocarbons. And finally, gravel, where we saw the picture. I took that picture on the beach in St. John, and there's lots of little rocks. Any questions? All right. Let's move forward into properties then. We're going to cover two types of properties: physical properties and chemical properties. Likewise, each of the property will be associated with a change: a physical change, a chemical change. In a physical change, you start off with one substance, something happens to it, but it's still the same substance when you're done. It just looks different. A chemical change, you start off with one substance and you wind up with totally new stuff. So, okay, this is water in the solid phase. If it melts, it drips. There's fog all around. That's water in the gas phase, etc. Physical properties, we're talking appearance, density, melting point, boiling point, whatever. Let's talk about our three states of matter: solids, liquids, and gases. We're going to address what's called the kinetic molecular theory that will explain why these things are the way they are. This is supposed to represent a solid. A solid, the particles of the solid are basically held in place by intermolecular forces, and they can't move. They get frustrated and they just sit and vibrate. In a liquid, the particles have enough energy that they can slide next to each other, but they can't get away. They're still stuck, but they're squishing around. A gas, we have no interaction at all between particles, and they're just zipping as fast as they can, and they keep going in a straight line until they hit the wall or each other. Solids will have a definite shape and a definite volume. Liquids will have a definite volume, but they'll take on whatever shape of your container. Gases don't have a defined shape or volume. They simply fill your container and things bounce around. We can go from solids to liquids. That's called melting. This will happen for a solid at a given temperature. We call that the melting point. Every substance that we know of has a unique melting point. You can see why in a minute, but the melting point is a unique property, physical property of a substance. We can also go from liquid to gas phase, that's the boiling point, and once again, that's unique to a substance. You can go from a solid directly to a gas called sublimation. That does not occur at a given temperature. It's a continuous process. Let's look at bromine. Bromine. Gee, I wish our periodic table was down. Kill my back if I try. This is bromine. Bromine is in the periodic table there somewhere. Has a melting point of minus 7.2, a boiling point of 58.8. This is a vial that was frozen. This is solid bromine down here. It started to melt, that's the brown liquid, and it gives off a gas, that's the gas filling the top of the vial here. Very toxic sort of stuff. All right, melting point is minus 7, boiling point of 58. What will it be at minus 20? Well, the melting point is minus 7, right? That's going from solid bromine to liquid. So minus 20 is less than that, so it's a solid. If we take it up to 80 degrees, at 58, that's the boiling point of bromine. Liquid bromine goes from liquid to gas. At 58 degrees, we're above that, so it's in the gas phase. And if we're right around 0, minus 0.12, remember, at minus 7, it melts. So we get up to 0, it's still a liquid. So think about melting points, boiling points, and whatever. Here's another little set of problems to help you with that. We have a pure substance that's 15 degrees above its boiling point. What is it? Solid, liquid, or gas? Now logically, if it's above its boiling point, it's got to be a gas, right? If you ever have trouble with these types of problems, think about it like a number line, okay? We have melting point, a boiling point, solid, liquid, and gas. We're 15 degrees above the boiling point, therefore it's a gas. Compound melts at 115, boils at 325. At room temperature, what is it? Well, here's our thing. It melts at 115, boils at 325. 25 is way down here, so it's a solid. Melts at minus 45, boils at 4. What is it at minus 36? People always have trouble with negative numbers. Here we are. Melts at minus 45, boils at 4 degrees. We're at minus 36, where it's a liquid. All right, so why do things have unique melting points and boiling points? I said that this had to do with what we call the kinetic molecular theory, and we're just going to touch on it. Basically, kinetic molecular theory tells us that every particle that exists, everything, has an inherent attraction for everything else. That's an intermolecular attraction. Think about it. Remember buckyballs? Little tiny round magnets? I think they've been banned because children would eat them and then die. But if you take a big ball out, they're all held together in shape by magnetic attraction, right? That's the intermolecular force. According to the kinetic molecular theory, this would represent a solid. And like we saw earlier, in a solid, the particles don't have enough energy to overcome the intermolecular forces. And so they just sit there. Everything moves, so it just shakes, but it sits there. If we put more energy into it, there will come a point where we have enough energy that the particles start to slip and slide relative to each other. That's a liquid. The temperature that this transition happens depends upon the intermolecular forces. And because those are unique for every substance, the melting point is unique for every substance. Likewise, if we continue to put energy in, we hit the point where we can totally break all of the attractions and we get particles just flying off, and that's a gas. Once again, the boiling point depends upon intermolecular interactions, and it's unique. So, for a gas, if you remember my little movie there, the particles are highly separated, so we can squeeze it down. That's how you compress a gas, because it's mostly empty space. Attractive forces are minimal, allowing it to take the shape and volume of the container. For a liquid, the closely spaced is not compressible. Attractive forces are intermediate, they slip and slide. It does have a defined volume, but not a defined shape. And finally, a solid, strong intermolecular forces, relatively fixed positions, not compressible, define volume and shape. Solids, liquids, and gases. Any questions? All right, let's continue to talk about properties. We're going to do the physical property of density. In lab, we will actually measure density, just to get you excited. Density is defined as the mass of a substance, typically in grams, divided by the volume of the substance, typically in cubic centimeters, although you can use any metric measurement for either of those. Any one. They both work. Cubic centimeter. Remember, centi is 10 to the minus 2. So there are 100 centimeters in a meter. A cubic centimeter is a cube that's 1 centimeter on all sides. If we take 1,000 of them, 1,000 cubic centimeters, in chemistry we refer to that as a liter. Liter. The abbreviation for liter is an uppercase L. 1/1000th of a liter is called a milliliter. Remember, milli is 10 to the minus 3. And that's exactly the same volume as a cubic centimeter. In lab, we will typically use milliliter to measure liquids and centimeters or cubic centimeters for solids. If we had exactly 1 cubic centimeter of gold and we weighed it, it would be 19.3 grams. Therefore, mass is 19.3, the volume is 1 cubic centimeter, the density, mass divided by volume, 19.3 grams per cubic centimeter. That's all the world density is. Mass divided by volume. Any questions? The density of water is darn near 1. In fact, if you cool water to 4 degrees centigrade, it is exactly 1, but only at 4 degrees. 25 degrees at room temperature, it's about 0.996. Mercury. We used to all be much more familiar with mercury. Mercury was fun to play with when I was a child. Yes, we played with it all the time. Unfortunately, it is now considered a neurotoxin, so poisoned an entire generation, but it was really fun to play with. It's a very dense liquid metal, 13 grams per cubic centimeter. Sulfur, about twice water. Iron, about 7.8. And these are gases. Now, expressed as grams per cubic centimeter, this is an uncomfortably small number. So quite often when you're dealing with a gas, a different set of units will be used, and it will be grams per liter. Remember, a liter is 1,000 cubic centimeters, so just multiply it by 1,000. You'll note that helium is much less than oxygen, and that's why helium balloons float. Now, this is something you've probably never seen. This is a gentleman holding a cannonball, and he's standing in front of this giant pool of mercury. Told you it was fun to play with. I hope he's holding his breath. What he's going to do is throw the cannonball into the mercury. And as he does, you'll note this cannonball, it's a real cannonball, it's just floating. Why is it floating? Density. The density of iron is 7.8. The density of mercury is 13.5. This is light, and it floats.
Can you go back and do that again so I can see that?
Sure. I think I can. And he drops it in.
Oh,
And
it's
it's
a
just
whole container of
a
mercury.
whole container.
Okay.
Yes. Yes, there's actually a picture that I have that I used to put in when I talked about mercury. But I decided finally that it was tasteless. Okay, so they use mercury in the processing of felt to make hats. Hence the Mad Hatter, right? So here was a picture of this guy with a pool of mercury that was 8 feet around, sort of thing, and very deep. And here was this person sitting on it, and just sitting on the mercury. Okay, you can do that. But unfortunately, he had worked in this mercury plant for far too long, and you can kind of tell that he was suffering the consequences. So I figured it was too distasteful. Couldn't show it anymore. But
So what
whatever.
does mercury do? Messes with your brain then?
Yeah, messes
Like
with your
I,
brain. Mad Hatter syndrome. Because they use mercury to cure the felt plants. All right. We have 250 cubic centimeters of a gas. It weighs 0.45 grams. What's its density? You can pull out your calculators if you want and play along. We remember, of course, density is mass per unit volume. We are given a mass and we are given a volume. All we have to do is set up the ratio. Mass divided by volume. Our mass is 0.45 grams. Our volume is 250 cubic centimeters. Do our simple math. And our units are grams divided by cubic centimeters. All right, here we have a rock. Now, the rock is in irregular shape. But we know it weighs 43 grams. We want to know the density of that rock. The problem is we know its mass, but how do we know its volume? You're actually going to do this in lab, not for the rock, but close enough. What you're going to do is take the rock and put it in a graduated cylinder with some water in it. So what you do is you start off measuring. Initially, we're at 22.5. We add the rock, and we go up to 45.6. Now, this is basically the experiment that Archimedes did. And he said, Eureka. You know the Archimedes story. Well, he was a Greek scientist sort of guy. The king had been given a crown, and it was supposed to be solid gold. The king was skeptical that they had taken gold and silver and mixed them together. So he wanted to know if it was truly gold, and he asked Archimedes to figure it out. Well, you don't really want to take the king's crown and melt it, do you? into a cube. So the story is that one day he was taking a bath, and as he stepped into the bathtub, it ran over. And he said, Eureka, I got it. Basically, his volume was displacing the water to an equal volume. So by adding our rock to our cylinder, and we know the initial and the final reading, the difference of that is the volume of the rock. So, mass divided by volume. Here's our volume of the rock, the initial and final measurements, and here's its mass. Do the subtraction, do our simple division. Remember, centimeters and milliliters are the same measurement, so we can express this any number of ways. I've done this in a couple ways just to show you. This is gram per cubic centimeter, right? With a little slash, means numerator, denominator. Quite often you'll see a negative exponent written instead. Means the same thing, divided by cubic centimeter. Milliliters and cubic centimeters are the same thing, gram per milliliter. Any questions? The density of ethanol is 0.79. Ethanol is the alcohol of consumption. We have 15 mils of it, and we want to know how much that weighs. Instead of just using our density formula, what I'm going to do here is use given, ratio, and find. We are clearly given that we have 15 cubic centimeters of ethanol, right? But what's our ratio? Ratio is the density. Grams divided by cubic centimeters. So, we can set this up. Our given is 15. Our ratio is 0.79 grams in 1 cubic centimeter. There's our density expressed as a ratio. Start off with our given. Multiply it by our ratio. Remember, a cubic centimeter has to be in the denominator. They cancel. And we do our simple math. 15 times 0.79, 11.8 grams. Any questions? How about significant figures here? The rule for significant figures when you're manipulating measurements is that you're looking for the number that has the fewest, because that limits your accuracy. So this has 4 significant figures, right? This has 3. How about the 1? The 1 is actually an exact number. It's not a measurement. It's a definition. Grams per cubic centimeter. We didn't measure the cubic centimeter. It's just a unit. Therefore, it doesn't count, and this is correct. All right, let's do yet another one here. Take this and just kind of work through the numbers. We are given a density. We have 999 grams. What's our volume? You can do this two ways, and we're going to do both. Simple way is to take the definition, mass divided by volume. Here we're looking for volume, so we have to solve for V, and we get that. So to solve the problem, what we have to do is take our mass divided by our density. Plug it in. Here's our mass, here's our density. Now, as you look at this, clearly we have grams in the numerator and grams in the denominator, so they cancel. What happens to the cubic centimeter? Well, the cubic centimeter is in the denominator of the denominator. So it's the reciprocal of a reciprocal. If you turn something upside down twice, you're back where you started, aren't you? So this equals cubic centimeter. So what happens here is this cubic centimeter goes up top, and that's our unit. The math is simply 1,000 divided by 13.5, and it's 73. Now go ahead and set this up using the ratio method. In the ratio method, this is going to be our given. This is going to be our ratio. And we're trying to find the volume. Well, our given is simply our 1,000 grams of mercury. Here's our ratio, that's our density. And we're trying to find cubic centimeters or volume. So we start off with our given, right? Plug in our ratio. And then we sit and look at it and say, oops, what's wrong here? The units of given must be in the denominator. So if you were just writing this ratio and you did it and you said, oops, what would you do? Simply turn it over. There you go. That's right. Now, grams are going to cancel. Simply multiply it out, and we get the same answer. The lesson here is that if you're setting up something and your ratio is upside down, just flip it over. Don't get excited, just flip it over. Any questions? One more simple question here. Liquid A and liquid B, density of 0.985 and 0.873. Which one floats? Ever made salad dressing? The oil floats, doesn't it? The less dense thing will always go to the surface, just like the cannonball did. Always remember the cannonball. Any questions? All right, this is a problem that is actually pretty much real time for lab. So you do a calculation and you say, all right, I need 2 grams of something, this is acetone. I know its density, but it's a liquid, and you're not going to weigh it out, you're going to measure a volume. So if you know its density, you can do that. Simply calculate the volume. Go ahead and set it up with the ratio method. Two grams is our given. Our ratio is simply our density. Grams must be in our denominator, so we're going to turn it upside down, right? Start off with our given. Flip this guy upside down. Grams will now cancel. 2 divided by 0.79. We need 2.53 cubic centimeters, which remember is the same as 2.53 milliliters. All the labware that we have will be measured out or calibrated in milliliters. But remember, a milliliter and a cubic centimeter are the same things. Okay. Typically in lecture, when we finish a topic that makes its way onto exams, I like to show exam questions. These are from old exams. Doesn't mean that you're going to get something that looks like this, but you might. So let's just look and see how you test on this stuff. Here we're given a substance. We have a mass and a density. What's the volume? Now we've seen we can solve this 2 ways, using ratios or just using the formula. You may use any way you want that makes it work. Let's just use the formula here. Mass divided by volume. Again, our mass is 93. This is our density. We're solving for V. So here's our density. If we take our density divided by our mass, we should get volume. Do the simple math. And we're 63.7. Always remember liters, 1,000 cubic centimeter in a liter, 1 mil, and 1 cubic centimeter are the same thing. We have a volume, we have a density. What's the mass? This is the ratio method. Here's our given, here's our ratio, cubic centimeters, cancel, multiply it out to get the answer. We could also take our formula, substitute in, there's density, there's our volume, divide density by our volume, and we get 74.24. Now, as I look at these, there's 74.24, that's that, and 74.2. Which one do I choose? These are measurements, aren't they? How many significant figures here? 3. How many here? 3. Therefore, we can't quote the answer as 4, can we? Now I'll be honest, this is Chemistry 100. I wouldn't do that to you. If you got close enough to get 74.2, I would be thrilled. But later on in life, you're going to need to think about significant figures. Let's do one more. What's the density if a sample has this volume and this mass? This is a very simple one. All we're doing is calculating density, mass divided by volume. Here's our mass, here's our volume. Do our division. And there we are. Once again, we rounded to 3 significant figures. Oops. All right. Let's go to the tutorial that's called something like Density 1. This is one you get credit for. And it's a fun one. It's a table. You will be given 2 of these things, and you will simply calculate the third. When you enter it, remember you enter numbers only, no units, whatever. Okay? Here's our mass, here's our volume, what's our density? That's simple. Mass divided by volume. Do the calculation, 1.37. Go ahead and do this one. We're calculating a volume. Volume is going to be our mass divided by density. Our mass is 93, our density is 1.87. Divide them together, we get 51.5. Once again, do not enter units. Calculating mass. Mass is density multiplied by volume. Density multiplied by volume, 54.7. I guess there is one more. Again, we're calculating a mass. We have a volume, we have a density. Mass is density multiplied by volume. Simply multiply the numbers, and there we are. Now there's also a density 2. Density 2 is either for 110 or for general chemistry. It involves lots and lots of metric conversions and stuff like that. It's great practice. If you want to do it, please do. But this is the one that you get credit for. All right, finally, let's wind up by talking about properties. We talked about physical properties, physical changes, right? Chemical properties are associated with chemical changes. Physical change, you still wind up with the same substance, chemical change, you have something totally different. A simple demonstration of a chemical change might be this. This is aluminum, and this is bromine. Aluminum's a metal. Bromine actually exists as the element, as two bromine atoms linked together. If we take and we mix these two together, a chemical change occurs. Now, this is a little beaker with bromine in the bottom. It's very volatile, it's a liquid, and this is a very poisonous gas. Here we have a little bit of aluminum foil. We're going to take our foil, dump it in there. Within a matter of seconds, you can clearly see that a chemical reaction is occurring. Light and heat are given off. Huge amounts of toxic bromine are escaping. And when you're done, we have a new substance. Around the top of the thing here, we have this white crystalline powder. The white crystalline powder is aluminum bromide. Looks like that. This is a chemical change. Aluminum bromide looks nothing at all, has no properties the same as these guys. Totally different substance. In chemistry, we're going to show this process, the process of a chemical change, as a chemical reaction. Chemical reaction, we will have reactants on one side, products on the other, and an arrow. Now, when we talk about reactions in more detail, we'll stress this again, but the arrow in a chemical reaction has the same properties as an equal sign. That means you must have the same number and types of atoms on this side that you do on this side. Also, interestingly enough, the mass on this side must also equal the mass on this side. So this is a chemical change. Physical change, icicles. In the spring, they melt. They drip, but it's still water. We can take water, however, run electricity through it, and separate water into oxygen gas and hydrogen gas. That's a chemical change because these are totally different substances than the water we start with. Any questions? We just said this. I just wanted to show a couple examples of chemical changes here. Potassium, remember potassium is a K, phosphorus is a P, is a very reactive metal. It's a metal at room temperature, but you have to keep it underneath oil. That's because it will react with the air, and it especially reacts with water. When it reacts, it will form potassium hydroxide and hydrogen gas. The little S, L, A, Q, and G refer to the states, the physical state. So this is a solid, that's a liquid, that's a gas, and AQ means aqueous solution. So potassium hydroxide is dissolved in the water. If you look at this, we have 2 potassiums here, 2 here. We have 4 hydrogens here, 1, 2, 3, 4 here, 2 oxygens, 2 oxygens. Same numbers and types on both sides. Now the fun part is to actually do this. Here is our potassium under a little bit of oil. This is water. What's going to happen is they're going to react. We're going to form hydrogen gas. But it's really hot. And there's oxygen everywhere. So the hydrogen will instantly react with the oxygen because of the heat, and it'll burn. So here's what happens. Going to take a little bit of our metal potassium. When you drop it in, you see the flame as it bounces around the surface madly. If you took a bigger chunk of that stuff, plopped it into water, it gets so hot, so fast, it explodes. So you have to be real careful doing this. Any questions? Let's look at one more chemical reaction. The hydrogen that we just saw, I said reacted with oxygen, it burns, and it forms water. Once again, gas, gas, and gas. 4 hydrogens, 4 hydrogens, 2 oxygens, 1, 2 oxygens. Same numbers and types. This is a balloon. The balloon is filled with hydrogen. This is the room. The room is filled with oxygen. And this is some guy with a little flame on a long stick. I did that when I was young and realized immediately I wanted to be a chemist. So much fun, except my balloon was much, much bigger. All right, let's look at a couple of these things. Determine are these chemical or physical changes. Take a gold bar, we hammer it out, and we make gold leaf. Gold, it turns out, is the most malleable of all the elements. You can pound it out so it's barely a couple atoms thick. It's amazing. But when you wind up with gold leaf, it's still gold, isn't it? It's just really, really thin. So that's physical. How about boiling water? We start off with H2O, don't we? Liquid phase. Wind up with H2O in the gas phase. But it's still water. How about if we do a barbecue? Take carbon, light it, we form carbon dioxide. Carbon and carbon dioxide are different substances, aren't they? This is a chemical change. Simple concept. All right, the exam questions. Which of the following is physical change? Lighting a match. Well, if we light a match, we start off with a match head, and we go through lots of flame and stuff, and gas is evolved. It's different, isn't it? That's chemical. Sugar and tea is simply going to dissolve. Melting of aspirin. Yeah, most people have trouble with that concept. Aspirin really is just a chemical, organic chemical, and it melts, just like everything else. We still have sugar. We still have aspirin. B and C are correct. What are chemical properties of carbon? Remember, a chemical property basically describes a chemical reaction. A diamond is still just carbon. If it dissolves in carbon tet, it's still carbon, just dissolved. Does it dissolve in water? Solid is just a state. Reaction with oxygen is a chemical change. Which of the following statements, compounds cannot be decomposed into elements? What did we say a compound was? It's elements stuck together, right? What you stick together, you can pull apart. That's not right. Elements and compounds are pure substances. Definition of a pure substance is that it's the same all the way through. It can be a compound, can be an element. So that's good. Elements but not compounds are pure substances. Well, we just said that's wrong, and clearly it's a B. Finally, in this question, I gave densities for 3 different metals, cadmium, copper, and zinc. Here is an unknown metal, volume of 15, a mass of 133. What is it? How do you do that? You calculate its density. What's the density going to be? Its mass divided by its volume. When you do the calculation, mass divided by volume, 8.92, it is copper. I guess there is one more. I thought we were done. There's a balloon, helium. There's its density. If the mass of the balloon is so-and-so, what's the volume? Again, simple calculation. Density is mass divided by volume. Mass